Great. Well, hi everyone. Thanks for being here with us today for this week's AFMS seminar. So today it's my pleasure to introduce our speaker, Dr. Mohsen Talei, who is a DECRA Fellow and Senior Lecturer in the Department of Mechanical Engineering here at the University of Melbourne. So Mohsen received his PhD at the University of Melbourne and has also spent time as a postdoc at UNSW. Mohsen has extensive experience, I think that's fair to say, in the research field of energy, focusing on low emission energy technologies. And he often uses HPC, so high performance computing, to achieve more reliable models for simulating cleaner gas turbines and reciprocating engines. So today he's going to be talking about some of this work. Please take it away, Mohsen.
All right. Thanks very much, Kath. Thanks for a nice introduction. And hello, everyone. And thanks for having me in this online seminar. As you can see from the title, I'm going to talk about high-fidelity simulations for cleaner gas turbines. And in this presentation, I'm going to talk about a couple of examples that how high-fidelity simulation can help us to understand issues that we face for developing cleaner gas turbines. And I'm also going to talk about combustion modeling using one type of machine learning approach, which is called gene expression programming. So I would like to start with the acknowledgement. Obviously, this is a teamwork, and none of what I present today would be possible without the help of these great people. I would like to start with my colleagues in the Thermodynamics Lab, Professor Michael Breer, Associate Professor E. Yang, and Dr. Robert Gordon, that I closely work with on several topics, and some of them will be discussed today. Professor Richard Sandberg is also my colleague at the University of Melbourne. We work together on using machine learning for combustion modeling. Professor Evet Hawks from UNSW, we've been working for quite a while on the combustion noise project. Dr. Bénédicte Cunot from France, she's also been a partner with us on using high-fidelity simulations. We have a code which was provided by Serfax, and we are collaborating with them on enhancing the capabilities of this code to make it faster and more efficient. I would like to acknowledge former PhD students who have done a lot of work in these projects. Dr. Ali Haqiri, who is a postdoc at the University of Melbourne. He did his PhD on direct numerical simulation of combustion noise. Dr. David Burzay, he's now a postdoc at Stanford University. He did a follow-on from Ali's PhD, working on combustion noise, looking at the sound sources in premix flames, and also looking at the impact of chemical modeling on combustion noise. Dr. Rahul Paluli, he has just finished his PhD. He also used DNS to look at the CO emissions due to flame wall interaction and flame cooling air interaction. And Dr. Dominic Ma, he also finished his PhD very recently during the COVID time, and he worked on using gene expression programming for combustion modeling. So I also acknowledge the funding bodies for this work. Australian Research Council, they have been supporting us through the DECRA Fellowship and previous discovery projects. We are a partner with the Future Fuel CRC, and we've been working on a number of projects related to hydrogen. The computational resources for the projects that I talk about today were provided by a National Computational Infrastructure, NCI, and the POSI Supercomputer Center, and we are grateful for that. All right, so let me introduce the Thermodynamics Lab at the University of Melbourne briefly. We work on a number of problems in the Thermodynamics Lab. Broadly speaking, all of them are energy-related topics. Engines and gas turbines are two forms of energy technologies that we are interested in. So We study these devices with conventional and alternative fuels. For example, hydrogen and natural gas are two forms of alternative fuels that we're looking at. We use a range of optical diagnostics to study sprays and engines. We do numerical simulation of combusting and non-combusting flows related to these two technologies. Powertrain dynamics and control is another area we are working on, and technical and economic analysis of transport and energy systems is also another research area in our lab. All right, so I am in charge of numerical modeling in the thermodynamics lab, and I briefly talk about the work that we do in that space. One group of studies that we do is related to gas turbines. The first one, which I'll talk about today, is sound generation by premixed flames, which is a major issue for introducing combustion instability in gas turbines. And I'll discuss that in more details in a couple of minutes. The second problem we're working on is flame wall interaction and flame cooling air interaction. These phenomena occur in a gas turbine combustor, and they've been known to affect flame dynamics and can play a role in emissions in gas turbines. So we also work on these problems. The third one is diluted flames with hot combustion products. These type of flames are used to control emissions. They are very difficult in terms of modeling, and the impact of these flames on emissions, especially when they interact with relatively cold walls, is not fully understood. So we use high-fidelity simulations to look at these flames more closely. The second group of problems are under reciprocating engines. So the first one is natural gas injection. So as I said, alternative fuels is an area that we are interested in, and we are working on injecting natural gas and looking at into an engine and looking at how the dynamics or gas dynamics inside the injector is going to affect the external flow and the mixing process inside the engine. The second type of problem related to engines is called engine knock. And this is a problem which prevents us from developing cleaner combustion in spark ignition engine. If you want to go to higher compression ratios, we have a problem which is an unwanted auto ignition. So as a result of very high compression, you have auto ignition happening, and that can cause what we call engine knock, which is a very loud sound. This creates vibration, can enhance heat transfer, and it can be quite damaging for the engine. So we're looking at this problem using high-fidelity simulation. Another group of problems is related to combustion modeling, which is relevant to both reciprocating engines and gas turbines. And finally, hydrogen combustion is another area that we are working on, because hydrogen is a clean fuel, especially if it's produced from renewable energy. But the issue with hydrogen is that it has very different properties, compared to conventional fuels like natural gas, and you cannot simply burn them in devices which are designed for operating with conventional fuels. All right, so that takes me to the topic of today's lecture, gas turbines. We know that they are the prime movers in the aviation industry. It's really hard to replace them with something like batteries, especially when it comes to long-range aircraft. And in the electricity sector, they play a significant role, as about 20% of the installed capacity globally is occupied by natural gas, by gas turbines, sorry. It's interesting to note the link between the aviation sector and the electricity sector, because there is a class of gas turbines called aeroderivative gas turbines. They are basically jet engines which have been modified to be able to produce electricity. And the reason is that the jet engines are quite advanced technologies, and a lot of gas turbine companies, they kind of do further development of jet engines and, you know, make them suitable for electricity generation. Once they spend a lot of money to make them, by having some modification, they can turn them to other classes of gas turbine. One of the nice advantages of gas turbines is their fast response rates. So you can actually ramp up and down the power very quickly. And this fast response rate makes them very suitable for frequency control, especially when you have an increased level of renewable energy in the electricity market. And renewable energy commonly causes intermittency. You need something like gas turbine to make sure that the grid works reliably and the frequency remains within the threshold that they should work on. So that's one advantage. The other interesting aspect of gas turbine is that if you combine them with the steam cycle, if you use the exhaust of a gas turbine in a steam cycle, you can get very high efficiency above 60%. And this is a remarkable kind of efficiency for a thermal plant. And especially if your thermal plant is operating with fossil fuel, you definitely want a high efficiency, okay? So there are much better options compared to other power plants. And finally, if you use hydrogen in gas turbine, if we manage to do that, and in some cases we are using hydrogen, you know, there are companies that have developed hydrogen gas turbines. And if hydrogen, as I said before, is produced from renewable energy, gas turbine can play a key role in decarbonization of the electricity sector. So lots of good news for gas turbines, but obviously there are some issues there too. So what are the problems when it comes to developing what we call cleaner gas turbines? So one important problem with gas turbine is that we want them to operate in lean premix combustion regime, because you want to mix fuel and air before combustion to get good combustion efficiency, and you can have a good control of your product temperature. So if you have a lean mixture, your temperature of the combustion product is relatively lower, and therefore you can reduce emissions such as NOx, the oxides of nitrogen, which is a strong function of temperature, right? But then we can face problems there as we try to go into these regimes of combustion. One of them is called combustion instability. So this problem is commonly initiated due to combustion noise. So the flame produces sound, and the sound produced by the flame, because it's in the confined domain, combustor is a confined domain, can reflect back to the flame, and this interaction can make the flame to fluctuate a lot and the flame becomes unstable as a result of that, okay? So this is an issue that occurs in lean premix combustors. The picture here on the left-hand side shows a burner of an existing gas turbine, okay? So what you see in the middle is a central flame, which is a premix flame. If you look at the rim of this burner, you can see a number of holes here, and these holes are there to supply fuel. So, and the type of flame they can produce are diffusion flames, basically flames which combustion and mixing happen pretty much at the same time, okay? And as I said, premix flame is something we want. Diffusion flame sometimes are needed, but in gas turbines, especially when it comes to combustion instability, sometimes they use these pilot flames. So they increase the mass flow rate of these pilot flames to change the combustion mode from premix to non-premix. And that's one of the ways they use to control combustion instability. But this is not a desirable mode of combustion in terms of efficiency and emissions. So the other type of problem we can get in gas turbines is CO emissions. So the picture on the right-hand side shows CO and NOx as a function of equivalence ratio. And you can see as we change the equivalence ratio, basically as we put more fuel into the fuel-air mixture, the amount of NOx emission increases, and that correlates with temperature. As we make the mixture linear, as we put more air into the mixture, you can see that in this case, especially when we have hard load, the amount of carbon monoxide increases, okay? And again, this is not something we want. If you look at the literature, there are not many studies that looked at this comprehensively, because it's a very hard problem. You know, in a gas turbine combustor, it's really hard to study how CO is being formed locally and, you know, what's the impact of the flame dynamics on CO emissions. But there are reasons suggested in the literature, some of them like insufficient mixing, inadequate residence time, which means we don't have enough time for combustion to be complete, and quenching of the combustion products or the flame with cooling air. For example, in a gas turbine combustor, we need to have cooling air to reduce the temperature of the product, and that can cause basically an increase in the amount of CO, okay? So these are the issues we face for developing a cleaner gas turbine. So what I'm gonna do today is talk about a couple of examples related to these issues. And we're gonna see how we can use direct numerical simulation to learn some lessons related to these problems. So example one, we'll talk about sound generation by premix flames. We will look at the mechanism of sound generation by these flames. And example two, we look at CO emissions due to flame cooling interactions. So we're gonna concentrate on one of these potential reasons in this presentation. And finally, I'm going to show you how we can use gene expression programming, which is one class of machine learning, to develop better combustion models with the help of DNS. All right. So I just introduced the DNS solvers that we've been using in this project, and you know the type of solver depends on the timing of the project and the type of problem we've been working on. I put them in two groups here. Detailed chemistry solvers, anti-mix chemkin is the one we got from Cefax. As I said, we worked with Dr. Cunot on improving the capabilities of anti-mix chemkin, and we are very grateful for their help. And in this solver, we can have a number of species, we can have reactions, and obviously the simulations are more expensive. This is more suitable for problems that we are interested in emissions, okay? The second group of solvers, we have used several codes here, simple chemistry, we have reactant and product only, so it's a lot cheaper than detailed chemistry simulations. We started with anti-mix, which is again a solver from Cefax. The second one that we used was called S3DSC, which is a modified version of the Sandia S3D code. The solver was modified by Dr. Karami during his PhD at UNSW. And the solver that we're using right now is called HipStar, which is a solver developed by Professor Richard Sandberg at the University of Melbourne. And we recently modified it such that we can do combustion simulation with this solver. All right, example one. So we're gonna look at sound generation by premix flames. So I'm gonna start with a video, and I would like to show you how changing the flame configuration can actually change the sound generation mechanism. So let me see if I can get the video to work. So my apologies if it was a bit loud, but hopefully I could communicate the message clearly here. All right, so this is a motivation to start simple. So we have done a 2D simulation similar to the video I showed you here. Just see if my pointer is working, sorry. Just turn on my pointer. Okay, so we have done a 2D simulation. It's a laminar flame. And because it's a symmetric problem, we're just simulating half of the domain, okay? So similar to the video, what we have is fuel and air coming in from the inflow boundary, and we have an open flame, which means we have outflow boundaries. The computational domain was set up such that we can avoid numerical reflection from the outflow boundaries. We excite the flame or perturb it using a velocity modulation. So we send the velocity perturbations in here. As a result of that, the flame wrinkles or responds to these velocity fluctuations, and that will produce sound. So we want to look at how sound generate, what the mechanism of sound generation is for this flame. As I said, this is a laminar flame, so the Mach number is relatively low, 0.08. The amplitude of excitation is 25%, so it's relatively high because we want the flame to respond to the fluctuations. The temperature ratio is 4, and the acoustic Reynolds number is 2000. All right, so I have to skip some of the results. We cannot present everything today, so I'm just going to present some of the key findings from the previous studies. So what we see here is the dilatation field of one of these flames at a certain frequency. And the dilatation field is commonly used by acousticians to look at the propagation of sound. It's not pressure fluctuation, it's the gradient of the velocity field. But in low Mach number flows, you can show that it is proportional to the time derivative of pressure. So it is related to wave propagation. The dilatation has an added value for us because we can also see the flame surface on the same plots. The flame is a region which features very high gradients. Therefore, you expect to get very high values of dilatation. So if you look at this flame, which I said is excited at a certain frequency, a couple of things happen here. So at some instant, you can see that the flame surfaces, so if I can show it with my laser pointer, the flame surfaces here collide with each other, and you can see that this is a strong source of noise, okay? So when the collision happens, you have a big circular wave being generated and propagates the far field. As a result of this event, which we call it a pinch-off event, you have a pocket forming, and the burnout of that pocket is also a source of sound. So you can see that sound is being generated as a result of this pocket burnout. So we call these two events pinch-off and island burnout, okay? And we did a number of studies to understand how they produce noise and what are the key flame parameters which contribute to the sound generation by these events, these separation or collapse events. But one of the key questions we had is that, okay, these are laminar flames. At the end of the day, you don't have a laminar flame in a gas turbine combustor, it's a turbulent flame. So are these events important noise sources in a turbulent flame? So this was a motivation for us to design a more expensive simulation. So we decided to do 2 simulations of turbulent premix flame. Again, the computational domain must be large enough to make sure that you don't have any reflections from the outflow. And also, we had to use what we call a sponge layer in the streamwise direction to damp the fluctuations as they leave the domain. Otherwise, we would get numerical reflections back into the domain. As I said, we did 2 simulations with different equivalence ratios. One of them is a stoichiometric, and the other one is a equivalence ratio of 0.7. What we decided to do is to make sure that the jet Reynolds number is the same between the two. So both of them have the Reynolds number of 5,300. And delta over D, which is the thermal flame thickness divided by the jet diameter, is also the same between the two. So in terms of flame turbulence interaction, they are in a similar combustion, similar regime. at the inflow, we had to inject some turbulence. So we used the DNS data of Wu and Moin, and we injected frozen turbulence, but rescaling it for a pipe flow. That's the these are the computational details for that simulation. Now let's look at one of the key findings. So this is again the dilatation field of the stoichiometric flame. And what you can see here, there are lots of monopolar sources of sound. And when I talk about monopolar, I mean these circular waves which are being generated in the flame. You can see that they are happening throughout the flame from close to the inlet. So from around here up to the tip of the flame, okay? And they have, different strengths, but it's not clear where they are coming from, okay? If you look carefully, you might be able to see these pockets which are burning here, and the pocket burnout is also a source of noise similar to what we had for a 2D flame. But, there are lots of other things happening here which are not clear. So the first step was to visualize this a bit more. And here I'm showing 3 examples of different events that can produce sound. The first one, I call it event A1. And what I'm showing here is the dilatation field, but zoomed in on this A1 event. So what we did, we looked at the pressure wave and we traced it back to get to the source to the noise source, all right? So what we see here is the zoomed in version of the dilatation and superimposed by the flame isosurface here. So this is basically a pocket burnout similar to what we saw for the 2D flame. It's not a symmetric one, it's not a spherically symmetric, but it's the same thing in terms of how it occurs, all right? The second event I'm gonna show you here is A2. And if you look at this flame surface evolution, this is similar to the pinch-off event, or we call it a tunnel closure. So you can see that you have 2 parts of the flame here that get separated, and then you have this tunnel, which is shown in this schematic, basically closed, and that produces sound, okay? So we can see the signature of tunnel closure in this flame too. The third one, which we haven't seen earlier, is event A3, which is close to the inlet. And this is where you have 2 flame surfaces which are almost parallel to each other. And as a result of the collapse of these 2, or collision of these 2 surfaces, you create a hole inside the flame. So you have the hole, and then you have a tunnel being formed around the hole, okay? So you can see a schematic of that here. So that's why we call this event a tunnel formation event. And the collapse of the tunnel will also produce noise after this event. So what is interesting about these turbulent flames is that you cannot really separate these events. In a lot of cases, you have these events happening very close to each other and in combination, okay? So again, one of the key questions we had was, okay, so we can see that these events making noise, and we can visualize it, you can trace them back visually, but the question is, can we quantify the significance of these annihilation events in terms of the overall sound generation, okay? So what we did next to develop an algorithm that can find these annihilation events automatically, all right? So that coarse processing tool also allowed us to identify the type of annihilation. So we can see, okay, this is a pocket burnout, this is a combination of pocket burnout and pinch-off, and all of those things. So the result of that study is presented in a paper that appeared recently. I'm just going to show you one figure from that paper, which is one of the highlights and relevant to today's talk, is basically the contribution of these annihilation events to the overall generated sound, okay? So the plot I have here is the sound pressure level as a function of a Struhal number, which is the non-dimensional frequency, okay? The solid line shows the DNS results. So basically, sound pressure level in the far at a point and at a point in space in the far field, and basically reasonably far from the flame. And the dashed line here is when you calculate the contribution of the annihilation events. Okay, when you identify these flame interaction events, put them together and see how much sound they produce overall. And what is interesting about that is that in the high frequency side of the spectrum, they dominate the sound generation here, and they still have a role to play in the low frequency sound, but it's not obviously explaining everything here. So the key message out of that is that you cannot, it's not easy to ignore annihilation and assume that they are similar to the rest of the flame surface. They are very different. They have very different dynamics, and I'll show you in a moment why I'm saying that. The other thing is that because these events have very short time scales, so when you have the collapsing happening, when you have the collision of flame surfaces, it happens very fast, especially at the when the flame are within a thickness of each other. And this short time scale makes them important on the high frequency side of the spectrum. So we are not surprised that they are the dominant noise source here on the high frequency side, okay? So what is the implication of that for modeling? So, okay, so these events are important in sound generation, but why should I care about them? So I'm gonna explain it using a simple theory. So one of the theories that have been used in the literature to develop combustion models is based on Mohsen linear theory. So a parameter which is very important for modeling is the flame displacement speed. And this is basically, if you imagine the flame as a surface, it's the flame speed relative to the unburned gas. And if you can predict this parameter, then you have your model in many cases, all right? So there is a lot of work in the literature to understand how the displacement speed varies as a function of other parameters, okay? And this linear theory is a starting point, which has been improved over years. And this is the most recent version of it, which describes ST over SL. ST is the displacement speed relative to the laminar flame speed. So if you have a laminar flame, just a 1D laminar flame, the flame speed would be SL. This is a function of a factor which is called Mohsen number, and another parameter which is called Kalowitz number, which is a function of flame properties. So flame strain rate, curvature, this is flame curvature, and ST appears here too, okay? So, and there are recommended values in the literature for the Mohsen number, okay? So now, if I look at the joint PDF of ST over SL and Kalowitz number, so ST star is a normalized version of ST. We don't need to go through that in this presentation, but it's similar to ST. If I look at the joint PDF, I can see that there is a negative correlation, right? But it's not easy to actually identify one number, one Mohsen length. And if we do the calculation, we will see that one single Mohsen number is not gonna work for the entire range of ST over SL. So what we did was to actually look at the annihilation events only, so filter them based on the values of ST over SL. So as I said, they have very short time scales. So what we did is say, okay, if the displacement speed is higher than a certain threshold, these values are related to annihilation events. And this is the way that we actually could identify them. If we plot ST over SL as a function of Kalowitz number for these events only, we can see that, as I said, the Mohsen number recommended in the literature cannot explain the behavior here. But one other thing that we did was to look at the two simplified annihilation events. One is a spherically symmetric annihilation. So if you have a flat sphere which is collapsing, and if I plot SD over SL as a function of Kalowitz number, I get one curve. And if I have a cylindrical flame, like a pinch-off event, and that cylindrical flame collapses, I get another curve for SD over SL. If I determine the Mohsen number for these two individual cases and take an average, I can see that that average number can explain the behavior of annihilation events. So this was quite encouraging, and we call that Mohsen number annihilation Mohsen number. So what I want to conclude from that is that these events need special treatment when it comes to modeling, right? They behave differently from the rest of the flame surface. So we have to be very careful when it comes to combustion modeling. All right. So this is the first example, and I just want to quickly go through what we're doing right now. As I said, we're looking at impact of chemical modeling on combustion noise. We look at developing reduced chemistry for accurate prediction of combustion noise, because so far we've been doing simple chemistry simulation. We want to see how having more complex chemistry is going to affect the sound generation. And we are interested in having combustion models in the context of large eddy simulations. So these are the works that are in progress, and some of them have been submitted to relevant journals. So example 2, now I'm going to talk about CO emissions due to flame cooling air interaction. All right, so you can see the signature of the first problem here. We would like to start simple all the time, because I reckon we learn a lot from simple problems, and then we can actually see the progression very nicely into more complex problems. Here again, what we've done is we've done a simulation of a 2D flame. So it's a symmetric problem. So we're just simulating half of the domain. This is like a duct. So we have a wall on the top of the domain. We have fresh gases coming in from the from the left-hand side, and we're anchoring the flame using a temperature profile like this. So the red line shows the temperature profile. The flame is anchored, and then we have a cooling jet coming from the top wall, interacting with the flame. Similar to what we had for the combustion noise study, we exciting the flame at the inlet, and we vary the frequency of excitation, we vary the cooling jet position. We also looked at the impact of what we call blowing ratio. So basically, what happens if you blow harder into the flame? If you increase the mass flow rate of the coolant, what would be the impact of that on the flame dynamics and also CO emissions? So we don't have time to talk about all of the results of that study, but I just want to highlight one of the key findings here. And that's the impact of blowing ratio. So if you blow harder into the flame, what will happen? And there's one graph that I would like you to have a close look. This is basically the graph we have here on the left-hand side. That shows the average CO mass fraction at x equals 6, which is this streamwise location. So is close to the exhaust of the domain. And you can see as you increase the blowing ratio, the average CO mass fraction, the red one is higher than the black and blue one, all right? So once the blowing ratio is above a threshold, it seems to increase the amount of CO emission. And this was quite interesting because this is something we had heard from industry that, you know, as you put, or, you know, there are papers which report that as you increase the amount of cooling air, you're going to get more CO. But this was for the first time observed. And what we think is happening is basically something related to Kondo effect. So as you increase the blowing ratio, you have a high velocity jet coming into the domain, and the jet is going to get a bit closer to the top wall, and it will impact the flame less. And this has an inverse effect on CO oxidation, because the more air you blow into the flame, you get more oxidation of CO, okay? But it seems that the jet dynamics play an important role here, and the exhaust CO emission will be impacted a lot as a result of that jet dynamics. The other part of the findings, which was interesting for modeling, was that if we look at CO mass fraction as a function of temperature in a region close to the wall, we get a scatter plot like this, all right? And what we did was to color the scatter plot with local equivalence ratio. And what I mean by that is that as you blow air into the flame, you're changing the local stoichiometry, right? So you had a mixture at a certain equivalence ratio coming in, and then you're adding more air to that. Obviously, the local equivalence ratio is going to be different to what you initially had, okay? And if we color it based on equivalence ratio, this is what we observe. It seems that, you know, for example, at high equivalence ratio, all the reds are sitting here close to the black line. And these black lines, the solid black lines, are actually the laminar flame solutions for individual equivalence ratios. So if we have a bunch of laminar flames at different equivalence ratios, that's how they look like in terms of YCO as a function of temperature. So it seems that the CO mass fraction can be modeled as a function of temperature and local stoichiometry. It's not a perfect model. I'm not claiming that you know, this is going to be an accurate model, but it seems that there is a correlation here. And we've done some further work, and the next step for us is to see what's happening in a turbulent flame. So what we've done is to set up a 3D computational domain in which we have basically two flame branches interacting with the top and bottom wall. The bottom wall doesn't have any cooling holes, and the top wall, excuse me, has a number of cooling jets coming into the flame, all right? And be looking at how these cooling jets are going to affect the flame dynamics compared to the other side, which there is no cooling jets. And what is interesting is that the same sort of observation we saw earlier, we also had this in this problem. And you know, the preliminary results of that will be presented at the next AFMC. All right, that takes me to the final part of the presentation, which is combustion modeling using GEP. Now that we have learned some lessons from the DNS, how we can actually use better combustion models. All right, as I said, the framework we are interested in is called gene expression programming. Is classified under evolutionary algorithms. Machine learning is very hot topic at the moment. There are many different techniques. We are interested in this technique for several reasons. This is basically, we use it as a regression tool, as a symbolic regression tool, okay? And what we like about GEP is that you can get a functional form that shows clearly the relationship between input and output, okay? It's not a black box, you can clearly see it. You can implement that function into the solver quite easily. And you can also put constraints on the functional form. For example, from the physics, we know that the function should look like this, but you know, there is one part of it, or there is a constant that needs to be evaluated, and we can have an analytical function for that constant. So these are the nice things about GEP, and we basically use it to develop combustion models. The framework that we have used is called flame surface density model, and it's in the context of large eddy simulation. In this framework, you have an equation for the progress variable with the source term on the right-hand side. So you can see our friend SD here again. And this is the one that we want to model. You can do a little bit of algebra and make some assumption, and then you can model it as a function of what we call the flame surface density. So sigma gen, which is basically the amount of surface area per volume, okay? And eventually, the function that you want to model is this one here, which we call it a wrinkling factor, is the magnitude of the gradient of progress variable filtered divided by the gradient of the filtered progress variable, okay? So this wrinkling factor is a parameter that needs to have a model. For some reason, my slides are going faster. And if you look at the literature, there are lots of algebraic forms derived from theory, and there are some tuning constant used in those algebraic forms. What we want to do, we want to see what GEP gives us based on the DNS data. So we used HeapStar to do the simulations. And as I said, the HeapStar has some nice features. For example, it's a multi-block solver. You can have Kerry linear coordinates there. So that allowed us to have a pipe flow simulation fully coupled fully coupled with the flame. So we didn't have to make any assumption about the velocity field. We didn't have to have frozen turbulence here. So we just had a boundary condition here, and then the turbulence was completely physical at the flame base. We simulated two different flames with different Kalowitz number, because these Kalowitz number are representative of different parts of the regime diagram. And we used the DNS data for training. We also wanted to look at the performance of the existing FSD models here. So we chose 3 models from the literature to see how they perform compared to our GEP models. In the training process, we tried different 3 options. One option was to use the low Kalowitz number flame dataset for training. So the model drive was GEP low. Then we used the high Kalowitz number flame data for training, and the model was GEP high. And then the other one was when we used both data sets for training, and the model is called GEP old. The idea was to see, if you train the model based on one data set, does it work for the other data set, okay? Because that's one of the limitations with machine learning, that you train it based on one data set, and as soon as you go outside the range, you don't see it working anymore. So there is a lot of information in this slide, but this is the third last one, so bear with me for a moment. If we want to look at the performance of different flame surface density models, there are different ways to do it. One of them is to look at the flame surface density conditional based on the progress variable, and see if we can actually predict the DNS one by using the model, okay? So I'm showing the low Kalowitz number flame and high Kalowitz number flames in these 2 groups. We have 3 rows, each of them representing one streamwise location, so 0.1, 0.4, and 0.7 of the total flame lengths. And we have 3 columns, each of them representing one filter size. So as we increase the filter size, we can see what's happening in terms of the model performance. So the black line shows the DNS results, okay? And if you look at the existing models, the only one which performs reasonably well is freebie model for large filter sizes, okay? The GEP ones, GEP low and GEP all, they both perform well for the low Kalowitz number flame, but GEP high is not doing really well in this case, which is not surprising. But if I look at the high Kalowitz flame data, what is surprising is that now I can see that the model trained based on the low Kalowitz number flame works really well here, okay? Which is something that we are still looking into, but is very encouraging in terms of modeling, because it shows that the low Kalowitz number flame has some properties that can capture the variation of the high Kalowitz number flame. All right. So I think obviously there is room for further work. What we have done so far is a priori testing. So just looking at the DNS data, filtering them, and see how the model performs. But if you want to do a real test, we have to actually implement the model in an alias solver and see how the model performs. So this is something we are working on. There is room for improvement, so we can include additional input parameters. As I said, for example, if you have annihilation events that need a special treatment, this is where the GEP can help you. And obviously, the more data you have, the more comprehensive model you can build. All right, so this is my last slide, and sorry if it took a bit longer than expected. I would like to end my presentation by this slide because, and it is a story about my PhD studies. When I was a PhD student in Melbourne, Tim Nichols, who he passed away, unfortunately, at a very young age. He was an academic at Cambridge working on vortex dynamics. He came to Melbourne and gave a presentation. And he said a story about his first day with Tony Perry. And Tony Perry, I think all of us know who he was. And Tony, apparently, he drew a diagram for Tim and said, look, we have these three things, theory, experiment, DNS. So I slightly modified it. I called it high-fidelity simulation. And all of them are complementary. So they are different tools helping us to tackle the research problems we are interested in. So, and in his presentation, Tim tried to show that, you know, sometimes DNS can help experiment. It's not always experiment helping DNS. And during my career so far, I've seen that actually how these things can actually communicate with each other, how theory can help experiment, or how can DNS or high fidelity simulation can inspire experimental work. I modified it even more and I put modeling in here because I think if we want to develop accurate models, we need all of them. My talk was about high fidelity simulation, but at the end of the day, we want everything, theory, high fidelity simulation, and experimental data together to make sure that we develop accurate models. So on that, that's the end of my presentation, and I'm happy to answer questions. Thank you.
Great, thanks so much, Mohsen. That was a really excellent talk. It was great hearing about your simulations, and I think you're doing some really important work here for the cleaner gas turbine type things. I like this final slide too. It's a really nice summary. And
thanks.
It's a summary, I think, that pops up in all of fluid dynamics too, basically trying to connect these different things together, these different techniques together.
Yeah.
We do have time for some questions. So if anyone in the audience wants to ask a question, you can unmute yourself and just go ahead, or you can put your hand up in the participant list and I can call on you, or you can just type in the chat. Any of those approaches are welcome. Maybe just when we're letting people gather their thoughts, I might ask a quick question. So I'm not sure if there's probably not a straightforward, easy answer for this, but in the first part of your talk, when you were talking about those 3D simulations, the two different 3D simulations, and you had an algorithm that was picking out the different types of annihilation events. So what is that algorithm? Is that quite complicated?
No, that's an excellent question. So what we did in that work, so let me go back to, basically what you can do is when you have an annihilation event, you always have a critical point, a point at which the gradient of the progress variable is 0, right? Mm-hmm. So you can say this is a point of collision. And you can identify the critical points in the whole domain, and those critical points will be basically the center of your annihilation event. If you calculate the Hessian matrix of the progress variable field, based on the sign of the eigenvalues, you can identify different types of annihilation events, okay? And so, I mean, if you're interested, the paper fully explained as the algorithm and how it works. So that was basically the idea, using at the critical points of the progress variable field and looking at the signs of the eigenvalues of the Hessian matrix.
Okay, cool. Thank you. That answers.
No problem. Yeah.
Okay, anyone in the audience?
Thanks, Mohsen. And I'm very interested in the question. And So my question is about your last slide. So you mentioned there are 3 ways to lead to a modeling. So for example, for me, like if I focus on the DNS in my PhD, then what is the pathway need to some modeling work? Because I don't have, I cannot do experiments and all the theories together. So can you give me, as a student, like, can you give me some guidance on this, the targeted to modeling? Thanks.
Yeah. I mean, that's a very good question. The problem is that we cannot do everything. So if you are very good at simulation, it's really hard to become really good at experiment. You probably need to get another PhD for that, right? So I think we should just continue to do things that we are good at. And if you have an opportunity to, for example, do experiment in the future, go for it. But the thing is, you know, and what I said at the beginning, this is a teamwork, right? And I've been pretty lucky to work in the Thermodynamics lab that we have, you know, I do simulation and we have experimentalists and we're working together and we learn about the problems, the challenges, and, you know, sometimes the conversation makes things a lot easier, and you get directions sometimes from experimentalists about how to set up your simulation, and sometimes you can you know, direct them about how to set up their experiment. Okay, so I think it is important that we work together rather than we try to do everything ourselves. Perhaps that's my, you know, answer to your question.
Yeah, that's perfect. Thanks.
How are we going? Any other questions from the audience?
I might ask one question, Mohsen.
Sure.
If you go into your 3-dimensional simulation of the cooling process, yes, this one, did you see any local extinction in your flame surface, or is it like a continuous flame surface?
Yeah, that's an excellent question. So the conditions we have simulated, we don't see any local extinction. So what we see is that the cooling air basically pushing the flame surface a bit lower. But we did some 2D simulations, and you know, if you push it really hard, you can actually see extinction events happening. But that one is a very hard problem in 3D. So that might be something we like to do in the future. And we think, like, if you increase the blowing ratio, at the moment, this simulation has a blowing ratio of close to 1. So we think if we increase the blowing ratio, we can observe that. But one thing, having said that, what you want in a gas turbine combustor is not extinction. What you want to have a, you know, cooling air, which is basically creating some a film of air, you know, above your liner to protect it. So you don't want your cooling air to interact with your flame much, but you in the final zone of combustion, you want mixing of cooling air with combustion products to lower the temperature.
Thanks.
No problem.
Right, any last minute questions? Otherwise, I think we might finish up there on time, which is perfect. And I'll just thank Mohsen once again for his talk. And I just might say, I think next week, wait till you get the email, but I think we might be on at 6 p.m. For next week. It's going to be a joint seminar with the Shield Folks. Okay, thanks everyone.
Thanks very much for having me.
Thanks, Mohsen.
Thank you.
Thanks, everyone.
Thank you, Mohsen.
Thanks, Julio.
Excellent seminar.
Thank you. Thanks.